Hello everyone, I'm Yixuan Cao from Shenzhen University. First of all, I sincerely apologize that I couldn't attend the conference in person due to personal reasons. Today, I'd like to present our work titled Tech-ASan, Two-Stage Check for a Jet Sanitizer. Memory safety violations are the 2023 CWE top 3 weaknesses, including spatial errors and temporal errors, may lead to system crash, data breach, and hijacked exclusion, etc. ASAN is a sharp weapon to detect such errors, offering excellent detection capability, scalability, and usability. Despite its popularity, ASAN brings high runtime overhead, mainly due to sanitizer checks. The shadow byte load in sanitizer checks is costly. Existing optimization methods focus on check elimination and check acceleration, but they either inadequately eliminate redundant checks or sacrifice detection capability. Our key question is, how can we reduce runtime overhead without compromising ASAN's core advantages? ASAN spares 1/8 of the address space as shadow memory to check memory access validity. Each shadow byte represents the state of 8 application bytes. 0 means that the entire 8-byte memory region is valid. K means that the first K bytes are valid and the last 8 minus K bytes are not. And any negative value means that the entire 8-byte word is invalid. Red zones are inserted around objects to detect spatial errors. ASAN doesn't fill red zones with magic value. ASAN performs runtime checks by instrumenting every memory access. These checks rely on loading shadow bytes, which is costly. Our goal is to replace most of these expensive checks with a fast magic value comparison in most cases, without costly shadow byte load. We present Tech-ASan, which combines check acceleration with check elimination. Our contributions include a novel two-stage check design avoiding shadow loads, loop-aware elimination algorithms, and a fully working LLVM-based implementation. Our evaluation shows significant performance gains with preserved detection capability. Let's talk about the difference between ASAN and Tech-ASan. We inject a magic value into red zones and freed memory. For all interesting memory accesses, we instrument two-stage checks. We also replace unsafe functions like string copy with safe variants. Compared to the latest version of ASAN, Tech-ASan covers wider, including character string functions like WCS-CPY. Our two-stage check works as follows. First, we do a fast check using the magic value. If it fails, we fall back to a slow check that reads shadow memory. To maximize performance, we carefully design the placement of the two-stage check logic. To store instructions accessing 1, 2, 4, or 8-byte memory regions, we insert the check logic before it. The point P in line 3 is cached, so this check is efficient. According to our study, more than 85% of memory accesses on spec CPU 2006 are stores, which were steeper optimization. So, for load instructions, we insert the check logic after it. This way, the loaded value is already in a register. Our optimizer removes checks safely. We eliminate unsatisfiable checks, remove recurring checks, and merge neighbor checks. Different from existing methods, on removing unsatisfiable checks, we additionally support to remove checks in loops. On GCC loops, our optimizer alone reduces checks by 18% and brings runtime overhead down to 102% from ASan minus 144%. Our evaluation answers the following 3 research questions. First, does Tech-ASan maintain the detection capability of ASan? Second, does it reduce runtime overhead of ASan? And third, how does it affect compile time and binary size? We adapt the Julia test suite to make the results deterministic. The adjusted Julia test suite has been released to the open source community for future study. On this suite, Tech-ASan maintains the same detection coverage as ASan and detects more violations hidden in WCS-CPY, confirming no loss in capability. We also test 20 real-world CVEs. Tech-ASan successfully detects all violations that ASan catches, verifying its robustness across real-world vulnerabilities. In addition, Tech-ASan is able to test large software with more than 3 million lines, which shows that it has good scalability. In terms of runtime, Tech-ASan reduces the overhead by 33.7% compared to ASan and 17.89% compared to ASan minus on spec CPU 2006 benchmark. In addition, aberration study shows that Tech-ASan with 2-stage checks alone incurs only 67.91% of runtime overhead. This validates the efficiency of our 2-stage check and optimization. Tech-ASan reduces binary size by an average of 14.79% compared to ASan. This is because we use function calls for slow checks and eliminate many unnecessary checks. Tech-ASan's binary sizes are within an acceptable range. The compile time overhead is about 29.52%, which is only 6% higher than ASan. For large-scale software compilation, Tech-ASan's compile time overhead is within an acceptable range. That's all for my presentation. Thank you for your listening. Once again, I apologize for not being able to attend in person. If you have any questions or would like to discuss further, feel free to email me. Thank you.